Hi, chemistry. Now that we've looked a little bit into ions, I want to return to our periodic trends and talk about our last periodic trend, which is looking at the ionic radius. So before we get into this, I want you to pause and tell me what happens to an atomic radius from left to right and why. What happens to an atomic radius top to bottom in a family and why? Pause here. Okay, so you may remember, hopefully you remember, that all trends within a period, all trends left to right, are driven by protons. This gets us back to our favorite law, Coulomb's law. Remember, where the force of attraction is proportional to the amount of amount of nuclear charge, which is number of protons, over, and it's inversely proportional to distance, to the square of distance. So if distance really isn't changing a whole lot, then and distance would change due to increasing energy levels, then the change in these periodic trends in a period left to right are going to be driven by atomic number. So as we go left to right in a period, the proton number, or the atomic number, increases by 1. So our nuclear charge is increasing by 1 left to right. And as a result, our atomic radius gets smaller. It starts kind of big and then it ends kind of small. So this happens across every single period. If we look at lithium versus neon, lithium is going to be the biggest atom in its period. Neon is going to be the smallest. This happens in the next one down, sodium versus argon. Sodium is going to be the biggest element in its period because it has the least amount of protons. Argon is going to be the smallest because it has the most amount of protons. Okay, so that's left to right. Now, top to bottom, we do have an increasing number of protons, but we also have an increasing number of energy levels. And distance has more of an effect because it's squared on the force of attraction. And so as we add energy levels, this atom is not able to draw in its electrons as closely, and so it's going to get bigger and bigger and bigger. Hydrogen is the smallest in its family, and as you go down the family, it's going to get bigger and bigger and bigger. Hydrogen has one energy level. Lithium has 2, and so lithium is going to be bigger than hydrogen. And so we see a trend of the atomic radius getting bigger from top to bottom in a periodic in a family. Now I have this nice little graphic here for you, and you can see that summarized here. Lithium is the biggest in its period, neon is the smallest, and that's true for every single row. It starts big and then it ends small because of increasing protons across that period. And then we also see the family trend where atomic radius is increasing. It starts small, gets bigger, starts small, gets bigger, starts small, gets bigger. The smallest one is going to be at the top of the family. The largest one is going to be at the bottom of the family because of increasing energy levels. So this is atomic radius. Now what we want to talk about today is the ionic radius. And the ionic radius is very similar to the atomic radius. It kind of uses the trend of the atomic radius with a catch. And so let's look at what that catch is. And the catch is how ions are formed. If we look across a period, ions are not formed the same way across the period. Lithium, beryllium, and boron, for example, they are going to lose an electron. And not only do they lose an electron, they lose an entire energy level. Let's look at that real fast. Here is lithium, beryllium, and boron. Remember, when lithium, beryllium, and boron, which are metals, form an ion, they are closer to emptying out their shell than they are at filling up their shell. And so they're going to tend to lose electrons and empty out their shell. So lithium's going to lose 1 electron to form lithium plus. Beryllium's going to lose 2 electrons to form beryllium 2 plus. Boron's going to lose 3 electrons to form boron 3 plus. Now, we've talked about that before, but what we haven't talked about is how when they lose these electrons, they actually lose an entire energy level. So the atom, the parent atom of these ions, has 2 energy levels. Well, the ion actually only has 1. And so the ion for these cations is actually going to be smaller. So cations are smaller than their parent atom that they came from. And this is true always. I mean, we use the second period as an example because it's the easiest one, but it's true for all periods. Look at sodium, magnesium, and aluminum. Sodium's going to lose 1 electron, losing its 3rd energy level. Magnesium will lose 2 electrons, also losing its 3rd energy level. Aluminum will lose 3 electrons, also losing its 3rd energy level. So while the parent atoms in the 3rd period all have 3 energy levels, the ions in that 3rd period actually only have, the cations actually only have 2. So again, the cations are going to be smaller than the parent atom. Now, if we look at the other side of the periodic table, let's look at the nonmetals. Okay, so nitrogen, oxygen, and fluorine. These are going to form negative ions. They're going to form anions. So remember, all these 3 are closer to filling up their energy level than they are to emptying it. So they're going to tend to gain electrons and fill up their energy level. So nitrogen will gain 3 electrons, filling up its 2nd energy level to form a nitrogen 3 minus. Oxygen will gain 2 electrons, filling up its 2nd energy level, making it a 2 minus. And fluorine will gain 1 electron, making it an F1 minus, filling up its 2nd energy level. So while the cations lose an energy level, the anions actually fill their energy level. They keep the same amount of energy levels as the parent atom. Not only do they keep the energy level, but they fill it. And so a full energy level is going to have a little bit more repulsion than a partially filled energy level. And so those anions that fill their energy level are actually going to get slightly bigger than their parent atom. Okay, so here is a break in the trend. Notice cations are going to get smaller than their parent atom. Anions are going to get bigger than their parent atom. And again, this is true for all anions, not just the anions in the 2nd period. If we look at the anions below, they do the exact same thing. Phosphorus gains 3 to fill its 3rd. Sulfur gains 2 to fill its 3rd. Chlorine gains 1 to fill its 3rd. Again, the anions are going to be bigger than the parent atom because of increased repulsion. They fill their energy level. Their protons don't change, so their size change can't be explained in terms of protons or nuclear charge. Their energy levels don't change, so their size change can't be explained in terms of increasing distance or increasing energy levels. We find a 3rd reason for a periodic trend here only, and that is increased repulsion. We can put the reason for cations decreasing energy levels, aka distance. Okay, I want to show you this in a different way, with a slightly different graphic. Okay, check out this graphic. So it takes a minute to kind of orient your eyes to what you're looking at. But the gray in all of these things is the parent atom. So try to train your eyes to look only at the gray. Notice that from lithium to fluorine, right? Gray, 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 gray. We see our atomic radius trend getting smaller. Our atomic radius of our parent atom starts big and ends small. Starts big, ends small because of increasing nuclear charge. Our parent atoms are going to start big and end small. That's our atomic radius trend. If you look at the ions, on the other hand, the ions don't follow this trend. Notice that lithium's ion is about here. Well, oxygen's ion, oops, that's not the ion, that's the parent atom. Oxygen's ion is actually huge compared to lithium's ion. And that's because oxygen is filling their valence shell with electrons. Lithium's getting rid of it completely. So we see the same trend of anions being bigger than parent atoms that we had on the last slide. Cations are smaller than their parent atom. We had that on the last slide. We can also kind of throw in a third trend here and say that cations within one period are going to be smaller than anions. And that one's new for us, right? Before, metal parent atoms would definitely be bigger than nonmetal parent atoms. But because cations and anions form in different ways, cations lose an energy level, anions fill their energy level, the cations in a period are going to be smaller than the anions in the same period. So left to right, our left to right trend within a period looks a little bit different for ions than it does for atoms. And we can kind of summarize it in 3 different ways, depending on what we're talking about. Now, another note here, atomic radius increases top to bottom, so does ionic radius. So really, when we're talking about ionic radius, you really only have to worry about the differences in the period between an ionic radius and atomic radius. There is no difference in a family trend, top to bottom. Atomic radius family trends are the same as ionic radius family trends. Notice they get bigger. The atoms get bigger. That's the gray. The ions get bigger. That's the pink or the blue. Atoms get bigger. Ions get bigger, top to bottom, because of increasing energy levels. Those increasing energy levels are going to dominate anything else that's going on with the atom. Okay, so those are that's the periodic trend for ionic radius. So let's do a little practice here. Tell me, let's go back up to a periodic table, since that's what you're going to have to look at on the test. Okay, so let's tell me this way. The ion of nitrogen, the nitride ion, versus the parent atom of nitrogen. How will those 2 things compare? And then let's do the sodium ion versus the parent atom of sodium. How will those 2 things compare? Let's do aluminum atom versus the phosphorus atom. How will those 2 things compare? And then let's do the aluminum ion versus the phosphorus ion. How will those 2 things compare? Okay, lots of things to compare. Check in, check your answers, work through this. This would be a good subject or content to kind of draw your way through the concept. That's going to help you process this a little bit more. Do some practice, look for other explanations of this same concept. Definitely bring me your questions and we can process through those together also. I will see you in class.